Hello. So yes, today is the final lecture. So what I'm gonna do is to continue with the discussion of non-Gaussianity, and then I want to mention a few problems or challenges to the theory of inflation. Yes, so, and then depending on how much time I have, I'll expand on that. So let us continue with the discussion of non-Gaussianity. So yesterday we said that what we already calculated was the Gaussian contribution. So essentially we considered the theory of perturbations, or the theory of perturbations of inflaton and metric during inflation, but we restricted ourselves to the quadratic part of the action. And an action which is that quadratic action could be decomposed into a sum of many oscillators. So we quantized that and we derived the two-point correlation function, but we understand that if we are dealing with a theory which is quadratic, then the distribution function that we get from this procedure of quantization would be a Gaussian distribution. So once we know the two-point function, we know the full Gaussian distribution, and therefore we know all of the correlation functions. These correlation functions, like for instance, higher order correlation functions which are related to the two-point function, we call them the disconnected contributions. They're contributions that come from the Gaussian part. And we also saw that if we consider the full theory will not be just quadratic in perturbation. There will be higher order terms in perturbation. So if we consider the action for zeta and gamma, so this zeta and gamma were gamma ij were we chose a particular gauge, and these were the variables that we were working with. So this action this starts from a quadratic piece, but then there will be higher order pieces. In particular, there will be a cubic piece. And these terms, if, for instance, if we try to calculate correlation functions, they contribute to the correlation functions. Or if we try to calculate the wave function, they give terms in the wave function which makes it non-Gaussian. Now, if you have a cubic term, it has it's nice in the sense that the cubic term in the action leads to a three-point correlation function. So usually, so what is nice about having a non-zero three-point correlation function? The nice thing about it is that it doesn't have any background. There's no contribution from the Gaussian part to this. So this correlation function will be non-zero. And that is in a sense, in a perturbative regime, that is the first signature of having non-Gaussianity or having interactions in our theory of perturbations. Now, what I'm going to talk about now is to talk about I want to give you first an example of a three-point function. So this three-point functions is the first signature of having non-Gaussianity or interaction. It's something that in cosmology, we are searching for. Like for instance, in Planck data, we have searched for these 3-point functions or analogs of this 3-point function. Remember, this zeta sets the initial condition for the fluctuations of temperature, for instance. So when we look for this quantity, it can be translated into a search for a 3-point function of temperature on isotropies of CMB. So we have actually looked for these quantities, and we have constraints on the magnitude of this. So what I'm gonna do is to give you a particular example, a very simple example in which we do get a non-trivial 3-point function. It is called local non-Gaussianity. And then explain what would be the prediction of the simple slow roll, single field slow roll inflation for the local non-Gaussianity. And then we continue. So, local non-Gaussianity. So here the idea is that why do I call it local? The idea is that the field that we want to observe, so here for instance zeta, suppose this field or observable field is related to another field which is exactly Gaussian. Let me call it G of x. However, it has a nonlinear relation, and the parameter of this nonlinearity I call it FNL. So zeta is G plus 1/2 FNL local, and this relation is a local relation, meaning that the value of zeta at point x is related to the value of this Gaussian field G at the same point x, but in a nonlinear way. Okay, so now if we have such a relation, and we know that G is Gaussian, let us determine what is the 3-point function of zeta in momentum space. What would be this quantity in that model? Well, the only thing that we need to do is to just Fourier transform this relation. The Fourier transform of a product is a convolution. And what we assume about G is that G is a Gaussian variable in the following instance. If I look at the correlation function of GK, G minus K, that is given by P of K. I put the prime so that I don't need to write the delta function. So there is a power spectrum of this Gaussian variable which determines the full distribution for this G, since it is Gaussian. And all higher order correlations of G are fully determined by this expression that I wrote. Now, what is the 3-point function of K? Sorry, the 3-point function of zeta. So zeta of K1, zeta of K2, zeta of K3. Again, let's put a prime and assume that K1 plus K2 plus K3 is equal to 0. Then it's a relatively easy exercise to see that this is equal to FNL times P of K1 times P of K2 plus P of K1 times P of K3 plus P of K2 times P of K3. Okay, so we get this expression. In particular, and this is FNL local. In particular, we can consider, one thing that I forgot. So this P of K, we want to take it to be something relevant, so similar to what we expect from inflation. So this P of K is something that goes as 1 over K cube up to a small slow roll corrections, so what we call tilt in the previous section. So remember, tilt or ns minus 1 was something small. So approximately, we have this 1 over k cubed behavior. So now if I consider the limit in which k1 is much less than k2 and k3, what happens in this limit? So let us first realize that here, of course, I put a prime, but if I didn't, there would be a delta function of momentum conservation. Would tell us that the sum of these three momenta add up to 0. This is, of course, just the consequence of the spatial homogeneity of the background. There's no spatial point on our background. Therefore, the total, or in other words, translational invariance. So the total momentum has to be conserved, which means that these three k's add up to 0, which means that I can put them on a triangle. So I have k1, k2, k3, which form a triangle. Now I want to look at the regime in which k1 is much smaller than k2 and k3 in magnitude. What does it mean? It means that I'm looking at a triangle which is, we call it a squeeze triangle. Right? So we have a squeezed triangle. In this limit, if we have this behavior for the power spectrum, then in this limit, the terms that have p of k1 are becoming larger because 1 over k1 cube is larger. So these two terms are much bigger than the third term. So in this limit, it becomes approximately twice FNL local times P of K1, P of K2. Now we can imagine that we have here, for instance, in our actual theory of inflation, we have this action and we calculate the 3-point function. We can try to ask the question of what would be the squeeze limit of the 3-point function that we get in this theory. And then that can be modeled by this local non-Gaussianity. So we want to determine this 3-point function in that particular limit. So how would we determine that during inflation? Well, we are going to use a trick that I talked about in the previous section when I was discussing why this particular choice of gauge and phi is constant and we parameterize the scalar fluctuations in terms of zeta is a good choice of gauge. Why was it a good choice of gauge? Because this zeta variable would remain conserved outside the horizon if we were in the attractive solution. So we want to use the same idea. The idea was that if I consider a long wavelength fluctuation of this zeta variable, it corresponds to, so remember this surfaces of hypersurfaces of constant time were the same as hypersurfaces of constant phi, and zeta would parameterize the shape of these surfaces. Now, we want to consider the situation in which we have a long wavelength fluctuation of zeta. Why am I talking about the long wavelength fluctuation? Because I'm taking one of the momenta, or one of the wave numbers, to be much, much smaller than the other ones. So the small wave number or momentum correspond to long wavelengths. Right, so you have a long wavelength fluctuation, so let me call it zeta L. And then we have two short wavelength fluctuations here. So we want to look at this 3-point function. So now the idea is the same as before. If I had an observer who lives here, and he does some local measurements, then for this observer, the local physics is identical to the background physics. This is the same history as if there was no fluctuation. But this long wavelength zeta perturbation doesn't really mean anything to this local observer. He cannot detect it. The only thing that it does is that if you remember the form of the metric, let me drop the tensor modes for the sake of simplicity. Or actually, I can keep. So the only thing that this line wavelength zeta mode does is that it rescales our coordinate. So basically, anything that we do here is identical to doing the measurements on an unperturbed background solution, except that we should use coordinate x tilde, which is e to the zeta long times x. Now, for instance, let us ask what is the 2-point function that this guy is measuring, or a correlation function that this guy is measuring. So we want to ask what is zeta, say the 2-point function minus x over 2, zeta and x over 2, but in the presence of this line mode. The condition that this x is much smaller than the wavelengths of the long wavelengths of the zeta line. So there is some wavelengths here. This is something that would be related to 1 over k1. And we want to take these x's to be much shorter than 1 over k1. So we want to determine this quantity. And I argued that this is the same quantity that you would calculate on the background, except that I should replace x with x tilde. Okay, let me go to momentum in space. And here I should put just P of k, right? So the correlation function in real space is related to the power spectrum in momentum space. It's a Fourier transform of the power spectrum. Okay, now I can do some change of variables of this integral. This x tilde is just some factor times x. So I can rewrite this as d3 of k tilde e to the I k tilde dot x P of e to the minus zeta L k tilde, where k tilde, so I define k tilde to be e to the zeta L times k. So the only thing that I did from here to here is that I just did a redefinition of k. And now I have to also put the Jacobian here. The Jacobian of the transformation is, so I go from k to k tilde. So I should put e to the minus 3 zeta L here. Now let us assume that this zeta L is a perturbation. So I want to expand in, linearize in zeta L. So that expression becomes d3. Okay, now I have an integral in terms of k tilde, but since k tilde is the variable of integration, I can just call it k. So here, what I do is that I just rename k tilde to be k, e to the I k dot x. And now I'm expanding to linear order in zeta, so I get 1 minus 3 zeta L minus zeta L d by d log k acting on p of k. Or I can put this factor of minus 3, I can absorb it in here by writing no. Yes. All right, so again, I just did some simple algebraic manipulation. All right, so we got this at first order, up to first order in zeta line. So what do we see? We are calculating a 2-point function of this zeta variable measured by this guy who lives in the presence of the long wavelength fluctuations. And we want to, we are evaluating that to leading order in this zeta line using this fact. So the physical input in this calculation was the fact that this zeta line fluctuation is locally unobservable. The only thing that it did was that we rescaled our coordinates. But then everything had to reduce to the calculation on the background, unperturbed solution. So we got this. Now what we do is that we correlate this object that we calculate with the zeta line, because now we see that the result does depend on zeta line in this particular way. So we are almost there. We correlate it now with some zeta k1. So this zeta line is the zeta in the position space. Now we correlate. It has some, can be expanded in terms of the Fourier modes. So we do that. We correlate it with zeta line. Of course, this one part does not have any correlation with zeta line because it doesn't depend on it. The 1-point function of this zeta is 0. This part has a correlation. So if we do correlate it, we get this 3-point function. Let me actually explicitly take care of momentum conservation. Minus K1/2. So what am I going to get? The correlation of this zeta K1, which is the line mode, with this zeta line gives me a P of K1. So now this K that I have here is actually the momentum of these modes. But remember, K2 is much bigger than K1. So this is approximately P of K2. This is this factor. So this K was the wave number of the short modes that we are evaluating. So K2. And then the rest is minus d by d log k of log of kq p of k. But this, we know what it is. This is what we call ns minus 1 in the previous lecture. So there's a minus 1. Therefore, the full answer is, let me try to fit it in here. The full answer is 1 minus ns times p of k1, p of k2. Assuming that k1 is much less than k2. So the corrections to this expressions are of order, the relative corrections to these expressions are of order k1 squared over k2 squared. Yes?
Could you repeat why this 2-point correlation comes from over this, when you go back around, is equal to this 3 correlation comes from that way? Why is the relation?
Oh.
Because I would expect that.
Sorry, there is no equality here.
Okay.
I'm just doing the following thing. I'm saying that this 3-point function, I can evaluate it in the following way. I can say that I first calculate the 2-point function of these two modes, which are short in the presence of a line mode, and then correlate that with the line mode. So if you like, I can write it like this. I write a correlation function of zeta k1 and the correlation function of these two short modes. And this is the part that I borrowed from the previous expression. So what do we learn? We learned that FNL local, which by which I mean the squeeze limit of the 3-point function that I get in this model, in the single field inflation, is given by 1/2, 1 minus ns. Now, I should say that there is another, I think there is another point of non-uniformity. So not everyone uses the same definition for FNL. Usually, FNL local is defined in terms of Newtonian potential, which means that, and that Newtonian potential has some related to zeta by some factor, some order 1 factor. So sometimes there has to be some overall factor that translates this expression, this 1/2 times 1 minus ns to FNL local that, for instance, you see in the in the results from, for instance, from the observations, like from Planck or WMAP. This relation between the squeeze limit correlation function and the tilt, remember this 1 minus ns is something, maybe I write it here because this is somewhat important. So we discovered that FNL local in single feed inflation is 1 minus ns, and ns was, so 1 minus ns was minus or 6 epsilon minus 2 eta, if I remember correctly. And observationally, we know that it's something small. So 1 minus ns is over the 0.03. So this local non-Gaussianity that we expect from single feed inflation is something of order of 1%. This relation, it was first derived by Mehrdad in the same paper that I mentioned before. It's sometimes called Mehrdad consistency condition. Yes?
I'm a bit confused. Where exactly are you assuming that there is single field inflation there? I mean, if you have any situation where you have a scalar fluctuation that has this power spectrum, will you get the same result, or it's always further?
That's a very good question. The answer is no. So there was a physical input in this argument, and the physical input was that this local observer and the things that he observes, he has no way of detecting the presence of the long wavelength mode. And that is generically not true. For instance, if you have a scalar field, some other scalar field, let's call it some sigma, and it has some value, in principle, scalar field is something measurable locally. I don't need to see its gradients. The absolute value of a scalar field is something that is measurable. Example is the Higgs field, right? It has a wave and it changes our physics, right? It gives mass to the gauge bosons. So generically, if I had some other scalar field, it would change the results of experiments that I would do locally here, and then this argument wouldn't go through. This is very special to the single feed inflation when I'm on the attractor solution. All right, so yeah, so this is tiny. The observation constraints that we have on this FNL local, the best one comes from Planck, which is something about the 5. But this is one of the targets of many cosmological surveys to try to get closer to this minimal prediction from the slow roll inflation. Why is it so interesting? It's interesting basically because of this physical fact. When we look at this squeeze limit correlation function, it's something that is sensitive to the degrees of freedom that are present during inflation. So here we assume a particular field content in which there was only a single field. if there are other fields during inflation, then they often show up in this correlation function. When you look at this squeezed correlation function, we see the imprints of those other degrees of freedom. So it's, in a sense, doing a kind of a spectroscopy for inflation, trying to detect what are the degrees of freedom that were active at that time. So by active, I mean they were light enough that they would affect, they would fluctuate and would affect the correlation function. Of course, if there are very heavy degrees of freedom, they won't have any important effect. So therefore, for instance, the measuring FNL larger than this, significantly larger than this would be a smoking gun for multi-field inflation, or at least non-attractor models of inflation. Yeah.
So local non-Gaussian is something demanded by this single field inflation model. It's demanded by this kind of.
Say it again.
Local non-Gaussian is something demanded by this kind of inflation models. I mean, because if the FNL is 0, for instance, you would have a NS equal to 1. So you would have a perfect scaling variance, and it's not what we observe.
So if, for instance, if we see that FNL local is 0, so imagine we go down, and we don't see this. This would really mean that there is another degree of freedom. Because we have already measured 1 minus NS. We know that this is non-zero. So if we measure FNA equals 0, that would mean that we are not in single field inflation. There is some other model of inflation, or maybe some other description.
Kind of model, they assume local non-Gaussianity.
No, there is no assumption. I'm just saying this is the definition of local non-Gaussianity. Local non-Gaussianity in the squeeze limit reduces to this result. And what I'm showing here is that in single field inflation, you have a unique, unambiguous prediction for the value of FNL. So if you see anything different than that, it's not the single field inflation. Okay, so now I can, yes, so that was one use of non-Gaussianities. It allows us to better distinguish different models of inflation. So for instance, let me just mention a couple of. So let me mention 2 possibilities. One is when we have multi-field inflation. So this is a situation in which we can get larger values of FNL local, larger values. But I'm saying larger because this is really small. So I could, in principle, I would say different. But since it is so small, we try to look for larger values. So these are models that can give rise to larger values of local non-Gaussianity. Now we can also consider models of single field inflation which have different self-interactions, like derivative self-interactions. Those models those kind of interactions would not modify this argument. So this argument goes through even if the model, the single field model that we write is non-standard. However, they can lead to other types of non-Gaussianity. So here I can have FNL local much larger than, I don't know, epsilon and eta. Remember this? Yes, so this FNL local from the single field. This was single field. In multi-field models, we can have much larger values, and this is something that is being searched for. I should also say that this similar kind of reasoning make this local non-Gaussianity relatively robust, even against nonlinearities that show up in the subsequent evolution. Like, for instance, in a structure formation, one can see that those subsequent evolution, even though it can be very nonlinear, usually much more nonlinear than what we discuss here, they do not give rise to local non-Gaussianity. So this is a relatively clean signal that can be looked for, even in the relatively dirty data, because it's orthogonal to other effects. So the other possibility that one can consider is, or non-Gaussianities would be sensitive to, is the self-interactions in the single field. So if I have derivative self-interaction, or derivative interaction. Let me give you an explicit example. So for instance, we consider this single field with the canonical kinetic term, right? And a potential. Now, you can imagine that this field has some derivative self-interactions. So for instance, there is a d phi to the fourth term in the action. Now, if this is our model of inflation, then this d phi to the fourth term would lead to cubic self-interactions for the inflaton, for the fluctuations of the inflaton. Why? Because this phi has a background expectation value. So if I write phi as phi bar plus the curly phi, then this d phi to the fourth interaction will lead to some cubic action for the fluctuations, which look like 4 phi bar dot divided by lambda to the fourth times phi dot cube minus phi dot grad phi square. And this cubic self-interaction would lead to a 3-point function, which we can calculate. This is, for instance, something that is relatively easy to calculate using the perturbation theory techniques, like, for instance, the one that you use in the exercise. Now, for instance, if we do this calculation, we can explicitly check that it does not change, does not affect the squeeze limit at this order. So in the squeeze limit, the contribution from that self-interaction would be of the order of the terms that I have dropped here. So again, because that argument would be valid even if I add this self-interaction. So there's a larger class of single field models that would satisfy the squeeze limit consistency condition. Yes?
There, when we computed the three-point correlation function, we can obtain it like computing the two-point correlation function and then making with the other.
Mm-hmm.
But there, with the two-point correlation function, together with the term with the derivative, we had the field.
We had the field.
The field there, together with the derivative term.
You mean zeta long times d by, yes, yes.
And then when we computed the three-point correlation function, like, I don't know if you remember right, but the 1 minus INS, it was only the derivative, right?
So this expression that I have here, right, d by d log k of log of k cubed p of k. This is what we define as ns minus 1. If you are asking what happened to this, what happened to this was that when I correlated with this zeta k, then I get a two-point correlation function between this and that. So that gave me this p of k1 here. Sorry, just a second. I should say that you didn't have to use these tricks. In principle, with enough mathematical power like Maldacena has, you could just calculate and get the result. And then he checked that it satisfies this argument.
In this scenario, single field theory, you have that prediction for the NLF in this squeeze approximation. And you just said that the derivative interaction also in these limits is the same.
No, it's not the same. Okay. It's, in this limit, the derivative interactions will not change this coefficient. They will be suppressed by order k1 squared over k2 squared. So they will be of order of these terms that I have neglected. It will be subleading to this result.
So in this limit, you could choose between these two kinds of population?
I cannot, no, because in this limit, these derivative self-interactions do nothing, don't make no difference. So both models give the same. Whether I have derivative self-interactions or not, the squeeze limit behavior is the same.
So you can disentangle these two kinds of population, this squeeze
No,
limit?
we cannot. If we want to understand about these self-interactions, we have to look at other configurations. So this was looking at the squeeze configuration. So usually when we go away from the squeeze limit, we call these non-Gaussianities that are not peaked in the squeeze limit, we call them equilateral shapes of non-Gaussianity. So in order to discover this kind of interactions, we have to look for equilateral type non-Gaussianities. Maybe I write the name here. So these derivative interactions lead to equilateral. Other questions? Okay. If there is no other question, I guess I'm almost done. So my plan for the rest of the lecture is to try to list some of the challenges to inflation. So this is completely changing the topic. So if any question that you have, this is the time to ask. Okay, so what are the challenges? One of the challenges is the flatness of the potential. So we said that we want this inflaton potential to be flat enough to get this the slow roll solution. So for instance, this first and second derivative had to be small. Now, keeping the potential of a field, a scalar field, to be flat enough is something that is relatively non-trivial. So there are three ways. So for instance, that's why we have the Higgs hierarchy problem or electroweak hierarchy problem. It's because we have the Higgs field is a scalar field, and it has a mass, but it has self-interactions. And naively from perturbation theory, we see that mass of the Higgs field is not protected against those interactions. It can be renormalized. And that's why we come up with scenarios beyond the standard model scenarios to make the small mass of Higgs protected. So this is a kind of naturalness argument. So the argument is that having the mass of this field to be small is something unnatural. Now, there is always a trivial solution to these unnatural naturalness problems, which is that you can, of course, get it by tuning. So it's not really a logical inconsistency, but it's something that we are usually uncomfortable or unhappy with. What are the other solutions? The other solutions that we know, or maybe some of them. One of them is to have shift symmetry. Or no, maybe let me first say the other one that I want to rule out in this case. So one of them is to have supersymmetry. This is another way to protect the potential or the mass of a scalar field to be small. Because, for instance, the radiative corrections in supersymmetric theories are being canceled between different fields. And to be more explicit, between bosons and fermions, and supersymmetry is a symmetry between bosons and fermions. However, this doesn't work for inflation because inflation has positive vacuum energy, and that leads to a breaking of SUSY, supersymmetry. So this is not going to work for us. The other solution that we know is to have a shift symmetry. So what does shift symmetry do? What it does is that if this field that we are talking about, like the inflaton field, has some approximate shift symmetry that is broken by some quantity which is small, then that is small. There is an approximate shift symmetry, and that a small parameter would be would control the smallness of the parameter would control the corrections. So let me give you a very explicit example. The explicit example is the QCD axiom. If some of you might be familiar with. So what is the story of QCD axiom? The story is that we have a field which has the following, or at least the relevant part of its interactions is the following. So axiom is A, it has a normal kinetic term. But then it is also coupled to QCD field strengths via the following coupling. A over F times G mu nu, G tilde mu nu, where G is the field strength for the gluon fields. And I'm contracting this repeated indices. So let me write it like this. This dual means contracting the indices with the totally antisymmetric tensor. So there is the QCD axiom is a scalar field that coupled to the coupled in this way to GG dual. And if it wasn't because of this coupling, this axiom would have a shift symmetry. So normally, if we calculate perturbative corrections to its potential, we don't get anything. We get 0. The potential is protected by the shift symmetry. However, there is a non-perturbative contribution from QCD, or from instantons, for instance, which implies that if we go to energies much below the confinement scale for QCD, that those non-perturbative effects would produce a potential for the axiom. And that potential is something of the form lambda QCD squared times cosine of A over F. So if we look at this action, it actually has an exact discrete shift symmetry. So this cosine that I have written here, it preserves that discrete shift symmetry. A going to A plus 2 pi F. But it breaks the continuous shift symmetry of the axiom. So this is a mechanism that produces a mass for the QCD axiom, which is a non-perturbative mechanism, and it gives some finite potential. So this model has no. If I give you this model as a low energy model for the axiom, which has a potential, this has no naturalness problem. It could very naturally arise. And now, okay, so now let's look at this potential. How does it look? Let me actually shift the center of the potential a little bit. So let's write 1 minus cosine A over F at the expense of adding some CC. So I have V of A, and now it's like this, oscillating. Now, for instance, I could look in the vicinity of A equal to 0. I could expand this potential in the vicinity of A equal to 0, and it would give me a master. So I would get 1/2. I would get a potential in that vicinity, which would look like 1/2 MA squared A squared, where MA squared is this lambda QCD to the 4th divided by F squared.
Lambda QCD to the 4th there.
Oh, yes, thank you. So Okay, so now we need just a little bit of imagination to generalize this to inflation, to assume that there is a dark sector with some non-abelian engaged theory, and then inflaton is coupled in such a way to that dark sector that produces non-perturbatively a potential for inflaton. And then if we go near the bottom of that potential, we get, for instance, m squared, phi squared potential with a mass that is produced non-perturbatively and it is protected. So at the level of doing just effective field theory, that seems like a resolution to this flatness problem. There are ways to get flat potentials. However, now let us think about various scales in the problem. So we can imagine a different situation. So if we want to zoom near the bottom and we talk about having some m squared, phi squared model for inflation, it means that this f, because here I got this by assuming that a is much less than f, right? But then we know that in order to get inflation, in order to have a small slow roll parameter during inflation, now we have to include gravity, right? We want the scalar field to roll in this potential, but now we want to turn on gravity and see if we get a slow roll solution. So in m squared, phi squared, for instance, now my a's should all become phi. Let me just make them phi. We need phi to be much, so what happens? We want phi to be much larger than m Planck, but it should be much less than f. So this decay constant, this f is called the decay constant of the axion. So this f parameter have to be much larger than m Planck to be able to realize the large field inflation in this model. So as long as we can do that, no problem. On the other hand, and as you saw, we are going in the direction that we might, the inflationary model that would be a description of our universe would not be a large field inflation, but it might be a small field inflation. And the difference between the two was that epsilon in large field inflation is relatively large, would mean that R tensor to a scalar ratio is large. And as we put upper bounds on R, epsilon becomes smaller and smaller, and S minus 1 is fixed, therefore eta has to switch sign. So we go from convex potentials to concave potential. So if we go now towards the small field inflation, then we want to actually take this F to be smaller. So we don't want to expand this. So this would be large field. So if we want a small field inflation, we want a concave potential, which means that we want F to be smaller, and we want the inflaton not to be, inflation not to happen near the bottom, but we want it to happen near the top, where the second derivative of the potential is negative. Now, okay, so this is so far okay. We can in principle assume that inflaton sits near the top and inflation happens there. However, this brings us to the second challenge to inflation, which is called the initial patch problem. So what is the initial patch problem? The initial patch problem is that, so if you remember when we discussed the background solution for inflation, we just did an analysis of homogeneous solutions, right? There were no spatial perturbations. We just considered a time-dependent field and found the conditions for the inflation to start. However, if we want inflation to be a solution to the horizon problem, that seems to be a little bit too much to assume, right? If we assume that initially we study perfectly homogeneous initial condition, then it seems that we have basically assumed that there is no, we have assumed the solution to horizon problem, meaning that we started from perfectly homogeneous universe. So what we actually want to say, and the founding fathers of inflation would argue, was that even if you start from some initial condition with perturbations in the phi field, so this is supposed to be, say, phi of x. So if you emerge from Planck scale with some random fluctuations, we want the inflation to start in some region and then expand it exponentially and make it our homogeneous universe. However, this region that we need, this small region that we need for inflation to start actually needs to be a bit larger than a Hubble size, a horizon size. So this arguments that things outside the Hubble distance, they are causally disconnected and they couldn't be homogeneous, they would also apply here. Why do I want to assume that there is this patch which is relatively homogeneous? Well, you could say that if it is some random initial condition, finally, in some infinite universe, you will find some region, some superhorizon region that is sufficiently homogeneous. And the moment you find it, inflation starts and expands it expands it exponentially, so we wouldn't even care what happens everywhere else. So those places that would satisfy this condition would inflate, and that's where observers like us could live. And this is seems relatively convincing, except if we are dealing with the small field inflation, because now here inflation had to start from some particular point in the potential. So if I have a potential and I need to sit right at the top of the potential, then for some random configuration, it's not clear that we will find this solution. Maybe these fluctuations that we have after some time, they make the field roll down before the inflation even gets a chance to start. So this is something that is, there has been interesting new developments on this topic. It's not a fully answered questions. But recently, because we have better tools and better methods to do numerical relativity, people try to do simulations of this result. Of course, this is the moment I relax the assumptions of homogeneity, the moment I relax the symmetries of the problem, it becomes immediately impossible to say much about it analytically. So one thing that people have tried to do was to try to do simulations, so try to simulate our universe, or this beginning of the universe, by considering it to be in a box, in a periodic box, which we assume to be large enough. We start from some initial condition that is relatively random, or it has large inhomogeneities, and ask for various potentials what happens if I evolve this inhomogeneous initial condition. So not very surprisingly, what one sees is that in the large field models, more or less regardless of what this initial condition is, the inflation starts. So even if on initial you have no patch that satisfies the condition for inflation to start, after a while this inhomogeneous initial condition will disperse, and then some patch emerges, and then it takes over. Then it doesn't matter what other regions do. They might form, just a second, they might collapse into black holes, so you will get an inflating solution plus a bunch of black holes here and there. Yes?
These initial conditions you are talking about, they are classical ones for the perturbations, or they're related with the vacuum selection of the quantum field?
So the initial, these simulations are fully classical. So what I'm considering is that I'm considering an initial value problem formulated on in a box, because numerically we cannot do infinite space. And for the initial condition for this scalar field that is going to be our inflat, I consider general inhomogeneous initial condition. And of course, metric would be, for metric also, there are some degrees of freedom that are constrained, fixed by the initial conditions on other degrees of freedom. There are also tensor modes that you can choose. So there are various works. Some of them have made more simplification, some of them less simplification.
But then, since you have small fluctuations, and
they are not necessarily small fluctuations. They can be big fluctuations. Yeah.
But then you need to assume, you said they are random, right?
Uh-huh.
So what is the statistics of them? You should be able to choose whatever you want.
Well, if I do numerics, I would try different distributions, right? So what do they do in practice? In practice, I have this field in a box. I expand it in Fourier modes, and I say that the Fourier modes in the box between this k and that k are excited with this Gaussian distribution, for instance, with amplitude which is non-negligible. And let it go. And what happens is that, yes, if we are in the large field models, then the fluctuations disperse and the inflation starts. In a small field models, not necessarily, because if the initial condition is, so let's think about it in real space. If the initial condition for the field that I'm choosing is kind of spread, then they pull down the field from the top. So in some cases, for instance, it doesn't necessarily stop. Here you need to put it more. So one needs a little bit of tuning of the initial condition for the inflation to stop. There are also interesting analytic results which of course need to make further assumptions. They can be thought of as, so if you might have heard about singularity theorems that in GR that prove, like Penrose singularity theorem, that prove under very general conditions on the energy momentum tensor that if some conditions are satisfied, you will have a singularity, for instance, at initial time or at late time. So there are similar arguments, similar in spirit, arguments that one can think of them as non-singularity theorem. They, under some assumptions, in particular that the universe is compact, like in this case we are in a box, that if we start, for instance, from an expanding initial condition, we cannot have an universal collapse or what is called a big crunch singularity. So there are also interesting mathematical works on this. I tried to give a couple of references about this. So this was the second. Okay, I have like 10 minutes, I guess. So the other challenge is something that is sometimes called swampland versus landscape. So this is a challenge which comes from the top. So what is the idea? The idea is that we might have effective field theories that look perfectly healthy as a field theory or effective field theory. But the idea is that, of course, we don't understand quantum field theory, quantum gravity as well as we understand quantum field theory. So the idea is that there might be perfectly fine effective field theories which, when we try to couple them to gravity, they are not acceptable quantum theories of gravity. Or in other words, let me say it more honestly, if you cannot get them from a string theory compactification. So a string theory compactification, it has some landscape of possible theories that you can get, effective field theories. However, that doesn't include all possible doesn't necessarily include all effective field theories that we can write. Some of them, some good EFTs are not good EFTs plus gravity or plus quantum gravity. Now, so this is the general idea. Of course, it's a bit too general. So so therefore, but however, there are some particular criterion that people try to find these borders between swampland and landscape by coming up with particular criterion on the low energy effective field theories that determine whether we are crossing that border between landscape and swampland. So, for instance, one of them is something called the weak gravity conjecture. Now, I'm not going to say what weak gravity conjecture is exactly, but I'm going to say what it implies. at least in some special cases, the simplest cases that we can imagine, the weak gravity conjecture is a conjecture that implies if you have an axion field that I discussed here, and I said that if I want large field inflation, I need the axion decay constant to be much larger than implied. Weak gravity conjecture is a conjecture that says that in healthy effective field theory, F has to be always less than the Planck. Right. So what it does is constrains this possibility. Now, I should say that these conjectures that so far have been made, they are usually not enough to kill all possible models that we can imagine. For instance, in this very simple example, remember I said that this axion field has a discrete shift symmetry. So this effective potential is, in some simple cases, one can calculate and get the cosine. But there can be more general situation in which it's not really a cosine. We'll have different branches of this potential. So that the periodicity or the discrete shift is preserved. However, if you are on one of the branches and try to go up, you continue going up, you don't go back. This is called monodromy. So for instance, in this situation, I don't need F to be super Planckian in order to be able to go very far up in the potential. So that's, for instance, a situation in which weak gravity conjecture doesn't say anything about. But then there are other conjectures. So for instance, there are something called a distance conjecture, which says that I should say that these conjectures are not coming, or at least not necessarily coming out of nowhere. There are some reasons behind them, some justification and some evidence from explicit string theory construction. So one general idea of this string theory construction is that the superstring theory is a 10-dimensional theory. So in order to get to 4D, one has to compactify. So we have to think about our 4D universe as being a large part of a manifold which has a smaller directions, other dimensions which are small and compact. And these are some consequences. For instance, so what is the idea? Say, for instance, the actual world was 5-dimensional. But this 5-dimensional world, this 5th dimension could be tiny and compact. So for big observers, that could be totally unobservable. So imagine the following situation. So I'm trying to draw the 5th dimension. And then we are observers that here we are big observers. We don't have enough energy or resolution to detect this extra dimension which has a finite size. Now, very often the fields that describe the scalar fields that appear in this string theory compactifications, they're actually describing the sizes of that internal manifold that we have. So that phi field, for instance, could be the size here. The width of this 5th dimension. Now one can understand why there is a distance conjecture. Of course, this is the width appropriately normalized. The idea of this distance conjecture is that this phi field is, if it's gonna move for or change, vary for a very large amount compared to the Planck scale, what it implies is that this size of the extra dimension that we have is becoming very big. And then this 4D effective theory that we came up with, for instance, the EFT that was describing our inflation, model of inflation, as this field moves, as this field moves over super-Planckian distances, this four-dimensional effective field theory breaks down. The world becomes five-dimensional. So we cannot use that effective field theory there. Now, so again, this might apply to some explicit models. It's not obvious why it applies to all situations or all models that we write. Why, for instance, all of the fees have to correspond to size of some manifold. Another thing is that we already know from observation that we are, even if the range of the inflaton field that we might need for inflation is not infinitely larger than the Planck scale, is something about the 10 or a few 5 larger than m Planck. This is the constraint coming from the tensor to a scalar ratio. We don't really need delta phi to be, actually this distance conjecture is, yeah, I don't know, it's too much small. So this condition is not very quantitative. It's an order of magnitude constraint, because in explicit models there can be different ranges that are allowed. So one can imagine that in some explicit model, that number that appears here is, for instance, 15 or 20. And that would be enough to get a large field inflation that describes our universe. Okay, so this, but however, I should say that this is a very active area of research. Now you might wonder why it is an active area of research given that it's so vague. Well, it's partly because I probably explained it in a vague way. But another reason is that we don't have many handles on quantum gravity. So this is very active because of the hope that by thinking about these ideas, we might understand better the theory of quantum gravity. And maybe we find its implications in the observations on the theory of inflation, and then from there to cosmological observation. Okay, so I guess I'm already past the time. I won't talk about eternal inflation, which is fine. Okay.
So people can ask questions.
My question is about this initial patch issue for inflation.
Yeah.
So should we expect quantum mechanics to play a role even in the initial conditions for the background? Why it's safe to do the simulation and to claim that this is a challenge if you are just treating the inflaton field as pure classical field?
Well, here the idea is that you imagine the universe emerged from some, I don't know, some quantum gravity regime, in a very irregular way. And we want to see how it evolves, whether inflation starts or not. Now, what we are worried about in this initial patch problem is large inhomogeneities, because if the field was homogeneous, then the background solution, the background inflation would start. So the thing that we are worried about is large excitations of the field. But when we are dealing with large excitations of the fields, then that's the limit in which quantum mechanics becomes the approximation, classical approximation to quantum mechanics becomes better and better. So it's because of the nature of the problem that we are dealing with that we don't worry much about quantum fluctuations in that region.
So is that the same as asking how it's possible from this quantum regime to get large fluctuations? So is equivalent? Is the same problem?
No, I'm not dealing with any quantum regime. I'm agnostic about that. That's why I'm saying let's assume the universe emerged from that regime in some totally irregular way. Let's ask now, can inflation start or not? Now, this totally irregular initial condition, if it would be a challenge for inflation if it has large perturbations. But those are the perturbations that you can treat classically.
No, but yes, I understand. But when you say that, it seems that you are already inputting the challenge into assumptions for the regularity of the initial conditions. You are already allowing the problem to came from the quantum regime. So,
well, I guess I'm not making any assumption. I'm trying to be very generous. I make no assumption about this initial condition. No.
But you assume that they are large, for example. You are allowing them to be large, for example.
Well, of course,
when
I say I allow large perturbations, that is a more general situation than not allowing them, because a perfectly homogeneous configuration is a subset of configurations which are fully general.
Okay.
Like, for instance, when I said I put this distribution for the perturbations to be some Gaussian with the widths, right? One of the configurations within those is a perfectly homogeneous configuration, but it's a very incredibly unlikely configuration within those. But I'm not excluding that possibility. It's just the easiest possibility when there is no problem. But I want to understand the hard problem.
Any further questions for Mehrdad?
Yet on the initial patch problem, I don't understand quite well how can you be general about this? I mean, about these initial conditions. Like, probably you always can find some condition that's messy enough that it will not work. You will not get inflation as we want. So, like, where you draw the line? Where?
That's a good question. Well, maybe. So, for instance, in some cases, there are actually. So, if you want to be very precise, then that's when the mathematical theorems are useful. So, for instance, you can see that there are actually some set of assumptions that forbid a global recollapse. If you want a very sharp statement. Otherwise, yeah, I don't know. As long as some random initial condition 50% of the times gives inflation, I guess I'd be happy.
More questions for Mehrdad? So if not, let's thank Mehrdad for this very nice set of lectures on inflation. I want to say something because we are inviting Mehrdad to give a seminar, right, on the spin of black holes. So it's tomorrow. I'm not sure what time yet. 5 maybe, 5-ish.
Yeah.
So it's nice because Mehrdad is here, so he can talk about his work. So it's about spin of black holes, right?
Yeah. Primordial black.
Primordial black holes. So this is going to be tomorrow. I'm going to announce it properly later. Sorry.
Okay. Also, thank you for your questions and attention. Your derivation of another sentence.